Good day, everyone. Today's lesson is on exponential growth and decay. But in this video, I'm going to explain to you exponential growth first. So let's begin. If a quantity grows by a fixed percent at a regular interval, there is exponential growth. In other words, it is a pattern of data that shows greater increases with passing time, creating the curve out of an exponential function. And since we are talking about exponential function, our equation is y is equal to ax to the t, where y is your final value or amount, a is the initial value, t is time, and x is the determining factor here if it is a growth or a decay. And for this matter, it is our growth factor. And since we have exponential function, so our exponential growth has a shape that looks like this. So if this is your xy plane, so this is your y-axis, this is your x-axis, then our graph or the shape of our exponential growth will be increasing. So it will be like that. Another definition here, we have exponential growth occur when the amount of each stage is multiplied by a number, greater than 1. So it occurs when the amount at each stage is multiplied by a number greater than 1. And that number is your growth factor, which is 1 plus r. This is your growth factor. And it's actually equal to your x. If you go back to the original equation, y is equal to ax to the t, then this x here is just equal to 1 plus r here. They are the same. So if you use the equation y is equal to a times 1 plus r to the t, then your a is still the initial value, r is your growth rate, so it is expressed in percent or in decimal point, and then of course this is actually your t, that is your t here, is your time. Let's have some examples here. A population of a town in 2016 was estimated to be 35,000 people with annual rate increase of 2.4%. What is the growth factor for the town? Write the equation to model future growth, and in 2020, what is the estimated population of the town? Now, let's begin with writing our equation. Since it is an increase, definitely it is growth. So you have solution Okay, for your solution here, say letter A, you have your growth factor. So what is our growth factor? If you go back to our equation, y is equal to ax to the t, or you have y is equal to a times 1 plus r to the t, then x or 1 plus r is our growth factor. So we can say that x is equal to 1 plus r. And let's go back to our problem. You have 2.4. You have this 35,000. And of course the year 2016, that is where your initial population is 35,000. Okay, so 2.4, this is your R, 35,000, which is the initial population, that is your A, and of course this is the year. Now 2016, later we will go back to that let's have our growth factor first. So this is equal to 1 plus your R is just equal to 0.024. Okay, so you will have 1.024, and this is your growth factor. Then let's have letter B. Write the equation to model the future growth. So y, you have your A here, and you have your R, or you have your growth factor. So you can just have y is equal to 35,000 times 1.024 to the t, and that is your letter B. And then letter C, in 2020, what is the estimated population of the town? Now that's why I have this 2016, because this is relevant when we want to find time. So from 2016 to 2020, our time is 4 years. So we just substitute t, which is equal to 4 years, here in our equation. So we will have y is equal to 35,000 times 1.0024 to the fourth. Our t is 4. So simplify that. You can just plug this into your calculators. Then you will have y is equal to 38,483. And this is now the estimated population by the year 2020. Now let's have another example. A sample contains 1,000 counts of bacteria. The bacteria double every 20 minutes. At this rate, how many counts of bacteria will there be in 3 hours? Okay, So let's examine, our problem. What is our initial count of bacteria? You have here 1,000 every 20 minutes, and this is very important. It double every 20 minutes. So at this rate, how many counts of bacteria will there be in 3 hours? So 3 hours here is our time. This is our initial count, and then double every 20 minutes. So our growth factor is double every minute. So every minute there will be 2 to the 1 over 20. Now you can do this. You can use this one and change t to 1,180 minutes. Okay, I'll show you that. So this is our growth factor. So this is the growth factor. Okay, 2 to the 1 over 20. And we use 180 minutes, that is equivalent to 3 hours. So you have y is equal to 1,000 times 2 to the 1 over 20 to 180 minutes. So you can cancel this out. That gives you 9. So your answer is 1,000 times 2 to the 9th. 2 to the 9th is 512 times 1,000. So that gives you 512,000. These are counts of bacteria. After 3 hours, so in 3 hours. Now, if we will just use 3 hours here, then we can also write that. Okay, another way of writing it, if we have 3 hours, we use 3 hours. This is for our t is equal to 3 hours. Then our growth factor will be, we can use, say, 1 hour has 3 times 20 minutes. Okay, so every 20 minutes, that is our growth factor, this one. So our growth factor then would be 2 cubed. So you will have, let's go back to our equation. You can have y is equal to ax to the t. So where your x is equal to this one, your growth factor is 2 to the x, which is 2 cubed. So you will have y is equal to 1000 times 2 cube to the third, because you have your t, which is equal to 3 hours. So you have, your answer is 1000 times 2 to the 9, which is just the same as 1. Okay. And they're the same. You can use that. Either of this will do, but it's up to you which one would you prefer, as long as you will be able to determine your growth factor. So like 1 hour has 320 minutes. So every 20 minutes it doubles. So it doubles 3 times. So that would be 2 times 2 times 2, which is 2 cubed. I hope you understand this lesson, and I want you to try to practice answering these questions here. In my next video, I'm going to discuss with you exponential decay. So when you say decay, there would be a decrease in the population, in the amount. So that would be our next lesson. Thank you, and see you on the next video.